Okay, so intersections of lines and planes. So let's find the intersection, if it exists, of a line and a plane. Well, in this case, we might want to consider three possible case scenarios. Number one, so we have a plane, and then we have the line that is, in this case, parallel to that plane. Well, in this case, these two entities are not going to intersect, so in this case there's no intersection point. So when we do the algebra that we require, well, there will be no point of intersection. Well, the other case scenario is that the line intersects the plane at infinitely many points in this case, and then in that situation we have infinitely many solutions, so infinitely many points of intersection. But the most typical one is when we have the line intersecting the plane at only one point. Well, this will be connected with equation theory that you learned back when you first do, intermediate algebra, when you first learned how to solve equations. So we will recall that in a second. So find the intersection, if it exists, of the line r of t equals 3 plus 2t, negative t, and 5 plus 2t, and the plane given by the equation 2x minus 5y plus 3x equals to 45. So, yeah, that should be a z. Yeah, thank you. Yeah, I don't know what happened here. So, silly typo. Yeah, 3. This is a 3z, all right? 3z. So number one, it would be a good idea to rewrite these vector valued functions as its components. So recall that the first component is the x component, all right? And so x of t equals to 3 plus 2t, y of t equals to negative t, and z of t equals to 5 plus t. I mean, I'm doing this just so you can have a visual of what are we going to do next, but ultimately you don't have to write this list of equations because, well, this is the x equation, the y equation, or rather components. All we're going to do here is plug each equation where it corresponds in the equation of the plane, and that's all that's going to be about it. For example, I'm going to start with the equation. So 2x plus, or rather minus 5, y plus 3, z equals to 45. Alright, all we're going to do is substitute the x equation where we see the x, substitute the y equation where we see the y, and substitute the z equation where we see the letter z. That's all we do. Alright, so that's going to be 2x, or rather 2 times 3 plus 2t plus minus 5 times y, which is negative t, plus 3 times the equation for z, which is 5 plus t, and that should be equals to 45. Alright, so well, let's distribute this equation, solve the equation. Well, that's 2 times 3, which is 6, 2 times 2t, that's 4t, and then negative times a negative, careful, that's positive, 5t, and 3 times 5, which is 15, and 3 times t, which is 3t, equals to 45. And well, this is a linear equation. This is a basic algebra linear equation. Combine the constants together, so that's 4 plus 5, that's 9 plus 3, is that 12t? 12t, and then we have 15 plus 6, is that 21? Equals 45. Subtract 21 to get 12t equals to 24, and t equals to 2. Alright? And well, let's do the connection here with the theory of equations from basic algebra. Whenever we have a solution, like x equals to 4. Well, that means that's the unique solution to the equation, and then in those cases we call that a conditional equation, right? Because that equation is conditioned or is subject to that solution. However, if you get something like 0 equals to 3, what's this? No solution, right? So in this case we have a contradiction. That means that in this case the line wouldn't intersect the plane at all, right? It's not the case because we have one of those conditional ones. How about when you get 3 equals to 3? Infinitely many solutions, right? That means that the plane is intersecting the plane on infinitely many points. Well, but they're asking us for the point of intersection, not for the value of t where the plane intersects the line. What are we going to do? Substitute t equals to 2 on the 3 equations in our vector valued functions, and well, you might argue about, well, that's gonna output a vector, not a point. Yes, well, you'll see. So r of t equals 3 plus 2 times 2 and comma negative 2 comma 5 plus 2, and this will output the vector. So 3 plus 2 times 2, which is 4, that's a 7, negative 2, 7. All right. Well, so that's still fine because we can recall that vector valued functions. Okay, let me do a brief picture here in 3D. That's fine. I'm going to do the picture in 3D. And suppose we have this curve right here. All right. These vectors that result of plugging into different values of t are vectors from the origin to any point on the line, right? That's the initial point, p initial, and just some q point that passes on the line. But this point that passes, or the curve, this point that passes on the curve, isn't it the terminal point of that vector? So that's why we can write down this vector as a point. All right. Just so when you're doing these operations, they're asking for a point, the intersection point. We are getting as an output a vector. Well, recall that this vector is the terminal point on the curve in 3 dimensions. Well, I mean, I did this as a generic curve, but ultimately this is a line. I should have drawn a line in this case instead. Okay, so let's see. What else? Okay, so for the next topic, let's look. So we already looked at the intersection between a line and a plane. Let's this time look at the intersection between two planes. Well, so in 3 dimensions, planes are either parallel or they intersect on a line. Okay, what's the picture? So I have 2 planes here, all right? These 2 sheets. Either they're parallel, they never cross at all, or if they intersect, it should look like this. All right, they look like this. But do you see the intersection? Isn't it the intersection a straight line? Well, that straight line in this case will be defined as a vector valued function in the form of some kind of function like this. All right. So those are the 2 possibilities. It's not like in 2 lines, for example, that is between 2 lines, either parallel, they intersect at one point, or they intersect at infinitely many points. So in this case, there's no way a plane intersects another plane at one single point, right? Because of the nature of the shape. So it's either they do not intersect, they're parallel, or they're intersecting one line in between. So let's see how that works. All right. So As for the angle between two planes, well, this one, the information that we're going to use to find the angle between them is the fact that every plane has a related normal vector, right? So if we have this plane with its corresponding normal vector, and then another plane with its corresponding normal vector, all we have to do is find the angle of those normal vectors, and recall that the coefficients of the planes are the components of those normal vectors. So, and another piece of information in this case that is very, very key here is that we are looking at the angle between two vectors to be between 0 and 90 degrees. In other words, so let me go back to the planes in here. So when we look at the intersection between two planes, yes, there's some obtuse angle and there's an acute angle. In this case, we're looking for the acute angle, not the obtuse angle. It's not like when we found the angle between the two vectors, we got an angle in between 0 or 180 degrees. So for between two planes, we'll look at the acute angle only. And in the case that when you do the inverse cosine to find that angle, if you get an obtuse angle, just subtract that value from an angle from 180 degrees to get the acute angle. All right? It's going to be a basic geometry operation, as you will see. And the second piece of information, well, that was for finding the angle between the two planes. But in this case, to find the intersection of the two planes, that line of intersection, this is found by solving a system of equations. Well, you'll see how is that going to work when we get to that part. So we have a couple of planes here, 2x plus 3y minus z equals to -5. And x minus 2y plus 4z equals to 1. Number one, they're asking us to find the angle between the two planes. Well, so number one, let's label the first plane as P1. That's our 2x plus 3y minus z. And that should be equals to -5. While P2, that's our second plane, which is x minus 2y plus 4z equals to 1. Each of these have a corresponding normal vector. Recall that the coefficients of the variables x, y, and z are the coefficients. Okay, let's label this as n1 normal. So that's going to be the vector 2, 3, and -1. And n2, the second vector that comes from the second plane, that's 1, -2, and 4. So far so good with getting the information. Alright, so well, to find the angle between two planes, it's the same as finding the angle between the two vectors. So that we get it from using the cosine formula. Recall that there's another formula, the one that involves sine and that involves also the cross product of the vectors. But we mentioned as well that we don't use that formula for two reasons. Number one, the cross product takes forever as opposed to a dot product, and also we have issues with the output or the range of the arcsine function that outputs from -pi/2 to pi/2. And to be safe with those angles, we prefer the cosine version, the one that involves the dot product, because that formula, the inverse cosine outputs angles between 0 and 180 degrees. So we will never get into situation of these negative angles. All right. Okay. Well, what do we need what information do we need? We need the dot product of the two vectors, which we will compute in a second, and we need the magnitudes of the two vectors, which we will also compute. Okay. So let's find the dot product.
We just always ignore anything to the right of the equal sign?
Yes, it's because it's only the coefficients of x, y, and z, the components of those normal vectors. So n1 dotted with n2, that's okay. Let's write the vector notation: 2, 3, negative 1, and 1, negative 2, 4. So multiplying this pairwise, well, 2 times 1 is 2, 3 times negative 2 is minus 6, and negative 1 times 4, that's negative 4. And that's going to give us 2 minus 6, which is negative 4 minus 4, negative 8. Alright, so that's our dot product. The other two pieces of information, okay, let's put a check on the dot product. So we need the magnitude of u and the magnitude of v. So the magnitude of u, that's the square root of the sum of the squares of the components. 2 squared plus 3 squared plus a negative 1 squared. And simplifying all these together, so that's 4 plus 9, that's 13 plus 1, 14, root of 14. Check on the second magnitude, on the first magnitude rather. And one more, that's going to be the magnitude of the vector v. So that's the sum of the components squared. 1 squared plus a negative 2 squared plus 4 squared. And well, what do we have? 1 plus 4, that's 5 plus 16, is that 21? Square root of 21. So we have all the information that we need. Alright. Let's just substitute these values that we got over here. So cosine theta equals the dot product, which is negative 8, over the product of the magnitudes, that is the square root of 14, over the square root of 21. And well, to get the angle between these two vectors, do the arc sign on both sides. Yeah, the arc cosine. Yeah, arc cosine. Alright. And well, so this should give us approximately 117.81 degrees if we do it in the calculator. But what's the problem with this result? This is an obtuse angle, right? This is not an acute angle. So, well, recall that these angles range from 0 to 180. So all we have to do is to find the supplementary angle by subtracting it from 180. And so, nope, not the obtuse. So theta equals to 62.19 degrees. In this case, this is the right one. This is the correct one, rather. But the acute. Right? For the second part of the problem, well, in this case, it turns out that two planes intersect. That means that's because there's an angle in between them, right? So in this case, they're going to intersect at some line again. Okay, let's go back to the visual here. So we are going to find the equation of this line right here that represents the intersection between the planes. Well, so, and actually, let me comment on this because there's going to be three possible answers, three different ways to express it, because in this case, what are we going to have? Well, once we set up the problem, so what are we going to do? So, intersection between two planes, whenever we want to find intersections, we want to set the two equations together, right? But there is some sort of an issue here. Well, not really an issue. In fact, that's fine. So set the equation of the two planes together. solve the equation for x, y, and z, but there's there's something weird in here. Number one, we have more variables than equations, right? And when we have that situation, that means one of the variables is going to be the free variable. So we should be doing the following. For those of you who are in linear algebra or that have already taken linear algebra, you have solved systems of equations and expressed the solutions as parameters in which you have a free variable, whether and it could be the c variable. Typically is the most common one because typically we write those x's and y's in terms of z's. But you can do it the other way around. You can write x in terms of y and z in terms of y, or you could do it the other way. Y in terms of x and z in terms of x, but the most common thing to do here is to express everything in terms of z. If you haven't taken linear algebra or you haven't gotten to that point, don't worry. Again, you're not expected to see. Well, once you see the result, this is going to make more sense. Well, so this is what we're going to do. So combining the two planes together, what I'm going to do, I'm going to eliminate x. I'm going to eliminate x so that's number one. And so to eliminate x, I would need to multiply the second equation by -2. So that's going to become, so the first equation remains the same, 2x plus 3y minus z equals to -5, and that second equation becomes -2x plus 4y and minus 8z equals to -2. Alright? Adding the equations together, the x's get cancelled, and we get 7y minus 9z equals to -7. Okay, let's leave it like that for now. On the second equation, okay, I'm going to write the two equations together again. 2x plus 3y minus z equals to -5. X minus 2y plus 4z equals to 1. Well, in this case, our goal is to eliminate the y's. Well, in this case, we need to do two operations at the same time. So number one, we need to multiply the first equation by 2 and the second equation by 3. Because the coefficients of y in this case are 3 and -2. So multiplying by the opposite coefficients, in this case with positive signs, because we already have the opposite signs, we don't need to multiply by a negative. So the system right here will become 4x plus 6y minus 2z equals to -10. 3x minus 6y plus 12z equals to 3. And combining the equations together, the y's cancel. This is going to be 7x, and that's plus 10z. 10z equals to -7. All right. So in this case, okay, so when we do the elimination method when trying to solve systems of equations, typically we get x equals a number, y equals a number, z equals a number. In this case, when we are getting new equations, well, so, and notice we cannot combine these two equations together because I would still have two equations and 3 total variables. So that's even if we come up with a smaller system, it's still three variables. So what we're going to do here is solve for z on both equations. So subtract 7y to both sides and then divide by -9. That should be z equal to 9/7 of y minus 1. And here when we solve for z for the second equation, subtract 7x on both sides and then divide by 10. That z equals to, oh wait a minute, no, I'm not solving for z. I'm supposed to solve for y. Never mind. Let me go back. So let's solve for y. So that, okay, let me do one step at a time. 7y equals 9z minus 7, and y equals 9 over 7 z minus 1. And solving for x, that's 7x equals to negative 10 z minus 7, and x equals to negative 10 over 7 z, and also minus 1. So what are we doing here? We're writing both y and x as in terms of z. So coming back to intermediate algebra or pre-calculus, when you got to the theory of solving systems of equations, these were called parametric versions of solutions, because this represents infinitely many solutions, right? In that case, we have the situations in which the planes intersected at infinitely many points. Well, isn't it the picture that we really have right here? But now we're doing this in a different context, in the context of having two planes and with their corresponding vectors and all that, something that we didn't do back in intermediate algebra or in pre-calculus. We didn't incorporate the vector implication, the vector behind this whole thing. Well, what do we do in this case? So, from here, the trick is let z equals to t. Alright, that is, plug it in here and plug it in there. We will plug in that value of z of t wherever we see the letter t, and this will become y equals to 9/7 t minus 1, and this will become x equals to negative 10 over 7 t minus 1. And now we have all the information to write down that vector valued function that describes this line of intersection between the two planes. Well, r of t, that's going to be our r of t, and the x component in terms of t, that's negative 10 over 7 t minus 1, comma, the y component 9 over 7 t minus 1, and what would be the z component? Just t, right? That was the free variable. And well, these again, these systems of these solutions right here might look familiar with when solving systems of equation 3x3s in the case in which the planes intersected at infinitely many points. In other words, we had infinitely many solutions. We just didn't have a single order triple like 1, 3, negative 7, for example. We had to express those infinitely many solutions in parametric form, and in this case, well, that parametric, those parameters they didn't tell you back then really represented the parametric form of the equation of that line. All right. So let's move on to the next topic. So we got what's next? So the next topic is finding distances between lines and planes. All right. So finding the distance between a line and a plane. So suppose, well, let's draw a plane. All right, let's draw the plane, and that plane contains the point P, and of course, as usual, this plane has a normal vector related to it, right? And well, so in this case, this is the distance. Okay, I need to specify this is distance between a point and a plane. This title I have in number 6 was a more general topic that we're going to do for the rest of the calculations and formulas. All right, so we want to find the distance from a point right here. This point, notice, is outside of the plane, up or down, whatever. All right, so that distance is going to be, well, this point, okay, let's first of all, this point can be away from the plane this way, that way, all right? So there's infinitely many possibilities to describe the distance between a point and a plane, but in this case we're going to look for one in particular. What's that one? The one that is closest to the plane, because this distance is further away than this distance right here, right? So in this case, well, which one do we find? The furthest one in this case. I mean the closest one from the point. Let's call this Q, and that plane. Okay, well, so how are we going to find this distance? Okay, so check this normal vector right here. This normal vector is related to the plane. Okay, so let me use this table right here as our plane. Then, so here we're going to have a normal vector, all right? A normal vector, a point anywhere above the plane or below. Let's just do the case above the plane. And well, the distance. Let's make this, okay, maybe not too high. Okay. So this is the point right here. And we're going to look for this distance, the vertical distance, the distance that forms a 90-degree angle with the plane, not the distance to here or there, because that's a longer distance. So we're looking for the shortest distance. So we are going to define a point, the initial point of the normal vector to that point that is outside of the plane. That's going to be, let's call it this distance, right? That vector PQ, okay? But we want to figure out this distance right here. We want this distance. We want that.
The green line one?
That's the vector that goes from the point P to Q. Point P, which is on the plane, and Q, which is not on the plane. Now, how do we find this distance? Isn't it? Okay, any ideas on how do we find this distance? Uh-huh.
It looks like a Pythagorean theorem.
It looks like, well, we derive this piece of information using the Pythagorean theorem somehow. However, well, we can find this because this distance from this point to the plane is the same distance here, all right? And in this case, regardless of where this normal vector is located from the point in the middle of nowhere, even if it's here, it doesn't matter. It's the same vertical distance regardless of how far it is. So the trick here is to use projections, because this distance d will be the same distance projected here, all right? So what we're going to do is find the projection of the vector PQ, that is the shadow of this vector in green, onto the vector n, which is the normal vector, all right? So that's how we're going to find that point, that distance. So that is the distance d. That's the projection of the vector PQ onto the normal vector that is related to that plane, which of course we're given the equation of the plane, the coefficients of the equation describe that vector that is normal. Well, so the formula for the projection that we did last time, well, that's the dot product between the vectors, and that's over the magnitude squared, that times the vector, the normal vector, all right? Well, so, but in this case, We want the magnitude of that distance. And you might remember from last time, from when we covered this this projection, we look at the scalar, the scale of PQ onto the normal vector. That was more like, okay, that's the distance, or rather, not the absolute value, it's the magnitude of the distance. That was simply the magnitude of the projection onto the normal vector from the plane, and that's simply the magnitude, or rather the absolute, in this case this is the absolute value of the dot product between those two vectors over the magnitude of that normal vector, because we want to make sure that for the numerator we have absolute value. We want to make sure that that distance is a positive value. Okay, and again, note P on the plane Q not on the plane. Right? Q is a point above, outside of the plane. And well, that's the formula that we have here typed actually, but I wrote it, just to show you where the formula came from. Okay? So let's do one example, see how we find a distance between the point Q2, the Q21, -3, and the plane x plus y minus z. All right. So number one, let's do a brief picture here. So a tiny picture here, and that's going to be a point P, one point that it's on the plane. We don't have that information yet. We don't have any information on what point lies on the plane, but I'm going to show you how do we get a point. Well, and we have as well that point Q, which is 2, 1, -3. And well, of course, this plane has a related normal vector. What is that normal vector? Wouldn't be 1, 1, -1? 1, 1, -1. Okay? But well, we need a point on the plane which is not given. And however, we can find any point, because again, it doesn't matter. Again, going back to the visual here. From the point that we want to find its distance to the plane, it doesn't matter what point I choose on the plane. That point will be the initial point of the vector, of the normal vector to the plane, and it could be here, it could be there, it could be here, but this vertical distance from the point to the plane and this distance right here, it's still going to be the same regardless of that point. Last time, let's use one of the tools that we used last time, in particular, how to find the intercepts of a plane. And well, when it comes to that, preferably, we find the intercept related to the variable that has the easiest coefficient. The easiest coefficient is 1, so we can use the X intercept of the plane. How do we find the X intercept of the plane? We make y and z equals to 0. So any point an intercept is the easiest choice. Right, this is key right here when it comes to when you go back, do the homework, and when you write this on your notes, this is key whenever you see a problem like this. So any point is fine, and it could be the x-intercept, the y-intercept, the z-intercept. It doesn't matter, because that initial point of the normal vector Also, keep in mind that vectors are free vectors, can be placed anywhere as long as they follow the same direction. All right? And well, so we're going to find the x-intercept in this case. For the x-intercept, so that's y equals z equals to 0. So that's x equals to 1. All right? And as an order pair, what's that order pair? 1, 0, 0. All right? So this point is going to be that point. All right? So that's going to be that point. So we already have all the information. Q, let me rewrite that point P again. 1, 0, 0. And well, let's find that vector P to Q, which we will project onto the normal vector. All right? So how do we find that vector? Isn't it terminal minus initial? 2 minus 1, 1 minus 0, negative 3 minus 0. So vector PQ equals 2 minus 1, which is 1, 1 minus 0, which is 1, negative 3 minus 0, which is negative 3. All right? I think we have all the information that we need. That is, let me highlight this real quick.
Is the one off the plane always going to be the terminal?
Yes.
Okay.
Yeah, the one not on the plane is the terminal, and the one on the plane is the initial, and it's initial for both the normal vector and the vector PQ, which we will project on the normal vector. All right, so let me highlight the vectors that we're going to use. This vector and that vector to find that projection. So number one, how about we find the dot product first separately. So PQ dotted with the normal vector, this will be PQ, which is 1, 1, negative 3, and the other vector, the normal vector, which is 1, 1, negative 1. Those are the coefficients of the plane again, right? We call it the coefficients of the plane. Those are the components of the vector that is normal to that plane. So that's 1 times 1, which is 1. 1 times 1, which is another 1, and negative 3 times negative 1, that's plus 3. And that's going to be 5. The dot product is going to be 5. We also need the magnitude of the vector, of the normal vector. Alright. And that's the square root of 1 squared plus 1 squared plus negative 1 squared. Those are the components. And that's the square root of 3. Alright? So we have all the information that we need. We want that magnitude of the projection. The magnitude of the projection is going to be the distance, not just the d, which is a vector itself. So in this case, this distance right here will be the absolute value of the dot product between P and Q over the magnitude of that normal vector. So that's going to be 5 over root of 3. And well, I mean, you might want to rationalize this denominator. That's fine. That's 5 root of 3 over 3. Okay. It's fine for small numbers like this to rationalize. Recall that for crazy numbers like the ones that we did last time, no need to simplify. Well, at least on the exam, you don't need to simplify those crazy numbers. On MyMathLab, you may need to simplify those. The MyMathLab algorithm, it's a little picky at times, and it's just going to tell you, although your answer is correct, it's not in the most simplified form. So, but I don't mind on the exam. So there is an alternative way to find the distance between a plane and a point. And this formula typically It's typically taught in a pre-calculus course. If you did it, that's fine. If you didn't do it, that's fine as well. So if we write the equation, the equation of the plane in this form, we substitute the x, the y, and the z of the initial point that we choose from the plane. Take the absolute value of that number and divide by the square root of a squared plus b squared plus c squared, which is really the magnitude of the vector, isn't it? So either way, it's fine. All right. What other situation we may run into? So another situation is finding the distance between two parallel planes. Well, in this case, they have to be parallel planes because, well, what if we had intersecting planes? Well, this distance is not the same as that distance, right? So that's why we have to consider two parallel planes. So the distance between them, it's the same at any different point. So let's find that the distance between the two planes. And well, notice the equations they both look almost the same. All right, the x, y, and z have the same coefficients, but the constant terms are different. All right, it's when like when we have equations like y, like in the intermediate algebra, y equals 3x plus 5 and y equals to 3x minus 7, right? We have two lines with the same slope but different y-intercept, right? So in this case, we're going to have the same, well, again, we don't talk about slope in 3 dimensions yet, but the intercepts for sure are going to be different. So that's why we're going to have the planes with the same angle, if you will. All right. So let's see. So number one, let's draw two planes. And let's choose a point P on the plane. All right, a point P on the plane, and a point Q on the other plane. Okay. So what are we going to do? Well, this plane has a normal vector. This one has a normal vector. And if you notice, this is really the same vector. Recall, vectors are free. You can place them anywhere. But as long as they're both in the same direction, that's fine. All right. So in this case, well, we are going to find this distance right here. This distance PQ again. Okay. Well, so not the distance. Rather, we will define a vector. Now, we will define a vector between P and Q. The distance that we want is this distance, right? And this distance, again, is the projection of this vector onto the normal vector. And in this case, the normal vector is the same for both. So, again, we're going to repeat the same process as we did from the distance between the plane and the point. But in this case, yes, we have two planes, but ultimately by means of, again, having 2 points. Well, we don't know. We don't know any points about the plane, and we cannot make a table of values to choose. I mean, we could, but that's a very exhaustive process. But again, take advantage of the intercepts of that plane. All right. Well, so in this case, between the x, the y, or the z intercept, the one that would give us the easiest numbers wouldn't be the y-intercept. I mean, we can use the x-intercept if you prefer. Make this to a 0, x equals 2/3. But we don't like fractions, right? Let's make this nicer to work with. So y-intercept, make x and z equal to 0, x equals z and equals to 0. That's and that's the point 0, 2, 0. What about the second plane? Find the y-intercept as well. What's the intercept?
0 to
Y-intercept. Again, x equals to z equals to 0, and that's 0, 10, and 0. All right. How about let me highlight with one color each, so you can see which one is which. This one corresponds to the second plane, and this other point 0, 2, 0, 2, 2, I mean 0, 2, 0 corresponds to the intercept of the first plane. Of course, I mean, another way to get a point on the plane, think of numbers, like think of three numbers, x, y, and z, such that multiply the x plus add the y minus subtract 4 times the z equals to 2. But see how that's kind of exhaustive to do? It's not like the best choice to do. Again, your favorite intercept will be your best choice. Well, so let's label, this is point P.
If you pick the y-intercept for one, does it have to be the same for the other?
It doesn't, they have to be the same, because if for some reason you get different coefficients here, they will no longer be parallel planes. What make planes parallel is that we have the same coefficients on the variables, but different independent terms in the same way that we did the comparison with the straight lines in 2D. Same slope, different intercepts.
If
Here,
x and y would have been available, could you pick like x on the first one and then y on the second? Like if it was x plus y.
You could choose, yes, in this case you could choose, for example, work with y-intercept here, and for whatever reason choose the z-intercept and get 10 over negative 4. Okay. And it's still a point on the second plane, but the thing is, it's fractions, and let's just pick the ones with integers. Well, in some cases, we may not even get the chance to work with integers, so there will be no way around than working with fractions. So, all right, so let's see. We have the vector PQ. Oh, I was labeling the point P, the point Q. Let's find the vector PQ. PQ, which is 0 minus 0, isn't that a 0? And 10 minus 2, isn't that an 8? And 0 minus 0, it's another 0. Okay, so we have the normal vector. And well, it doesn't matter where you get this from, because it's the same coefficients on both planes. That's a 3, 1, and negative 4. And well, what do we need to do? Find the dot product of between PQ and the normal vector. And that's going to give us 0 times 3, which is 0, 8 times 1, which is 8, and 0 times negative 4, that's a 0, that's going to be 8. And finding the magnitude of the normal vector, that's the square root of 3 squared plus 1 squared plus negative 4 squared. And that should give us, so that's 9 plus 1, that's 10 plus 16, is that the square root of 26? And writing this in the formula to find that magnitude of the projection, which is the distance between the two planes, that's the absolute value of the dot product. And again, we put absolute value bars in this case just to make sure that we end up with a positive quantity, and that divided by the square root of 26. And oh wait, no, anyway, in symbols, the magnitude of the normal vector. Now let's put numbers. That's 8 over the square root of 26, and this is an okay answer.